My name is Fujiwara from National Research Institute for Earth Science and Disaster Resilience, Japan. The title of my presentation is Shake Table Test of a Partial Model of a Roller-Supported Steel Roof, Part 2, Test for Reproducing Earthquake Damage. In Part 2, I report a shake table test of a partial gymnasium model with an RC substructure. The objectives of the test are to assess a friction damper and reproduce the seismic damage observed in 2016 Kumamoto earthquake. In this slide, you can see the shake table test plan. Similar to Part 1, the target structure is a gymnasium which had earthquake damage in Kumamoto earthquake. We extract a part of the gymnasium where many roof members were damaged and reduce it into 1/2.5 scale. For designing the test specimen, we take a law of similarity presented in the upper left table so that not only the size and configuration but also the dynamic behavior is similar. We reduce the cross-sectional shape of the RC substructure into 1/2.5 scale. We adjust the mass by installing steel plates so that to satisfy the law of similarity. We select the truss roof members from Japanese standard circular hollow profiles so that the compressive strengths are as similar as possible. Same as Part 1, the roller bearing has a detachable friction damper. In this slide, you can see the main measured items. We measure the relative displacement between the substructure and the roof as illustrated in the top left figure. We obtain the force acting to the roller bearing by the actual strains of truss members. Since the truss upper chord connected to the roller bearing may have large deformation, we measure the displacement between the both end nodes as shown in the top right figure. Same as Part 1, we take two types of input excitation, a sine excitation and a seismic excitation. You can see the acceleration time histories in the left side. In the shake table test, we conduct some excitations for assessment the friction damper first. Then we conduct a test for reproducing the earthquake damage observed in Kumamoto earthquake, specifically a crash at the roller bearing and buckling and fracture of the truss upper chord connected to the roller bearing. In this slide, you can see the result of friction damper assessment. In the left side, you can see the horizontal load displacement relationship at the roller bearing of 4 test cases. In the case of 75% seismic wave without the damper, a large displacement and crash have been observed. On the other hand, no crash has been seen in the case of 75 seismic wave excitation case with the damper. Here you can see the overview and result of the seismic damage reproduced test. Here we repeat seismic excitation where the input intensity increases gradually. I'll explain the detail of the test cases to 3, to 4, and to 5 later. In the 100% seismic excitation case, a crash at the roller bearing and buckling of the truss upper chord were observed. In the right figure, you can see the residual deformation. The buckling load is estimated as 66.3 kN from the measurement. In this slide, I'd like to show you the slow motion video of the 150% seismic excitation. As seen in the video, the upper chord has large deformation repeatedly and a local buckling at the center. Since no fracture was observed in the 150% seismic excitation, we conducted 150% excitation again. Here you can see the video. After 3.58 seconds from the start of the excitation, the connection bolt was fractured. Since the fracture time was before the main shock of the input acceleration, the upper chord might have large accumulated plastic deformation and be almost fractured in the first 150% excitation. The maximum floor acceleration is 1006 GAL and corresponds to the peak ground acceleration of 2016 Kumamoto earthquake. The original upper chord fractured at the local buckling located in the center. The difference of the fracture location might be caused by the size effect. I summarize my presentation as shown in this slide. Thank you for your kind attention.